Good morning, everybody. I had a not great weekend. All of my best plans got foiled, and it wasn't my fault. And I don't like counting on other people. So I was really looking forward to coming in this morning. Didn't get much rest. Nothing terrible happened, but it was annoying. It's a long story, but I was waiting on other. I had made plans back in May for things that needed to happen now, and at the last minute they got changed because I didn't have any power over it. Anyway, I'm the kind of person that plans ahead, and I've noticed that when you plan ahead and be proactive, you get punished by the people that procrastinate. So several things need to update you. So one of my goals for today was to make sure everybody had a chair in here. Okay, so I added extra chairs right into the room, and then several people emailed me over the weekend saying they had COVID. So in my family, we've got some immunocompromised people. So in general, what I'll do is I'll probably put a mask on if you come up and talk to me for any length of time, like face to face, right? Please don't be offended by that. I'm just trying to protect me and my family. Just so you are aware, right? Your fellow students are coming down with COVID. Looks like the peak is hitting us here in Fresno, right? So do what you need to do in order to feel safe and to be safe, right? This is my classroom's always an environment where people are welcome to wear masks or not, right? So do what you need to do. I'll probably wear this. I notice that if I wear it while I'm lecturing, then everybody just stops looking at me, right? Because I've become less human. So I try to wear it, not wear it while I'm lecturing, but like lab and everything else, I'll probably keep it on. I told you, I think in lab, if I remember correctly, that Physics 4B is not being offered next semester. I got my new schedule on Friday and I'm teaching 4B next semester. So I apologize, but for the last 23 years, we've never offered Physics 4B in the spring. But with the opening of the new science building, the department chair has figured out a schedule. We can offer Physics 4A, 4B, and 4C every semester. Okay? So I will, for the first time in my career here at Fresno State College, be teaching Physics 4B next spring. Okay? 4A and 4B. So I apologize for that misinformation. I did not know any of this, right, until Friday morning. Okay? So that is the plan, and we're sticking to it for now. I thought it was maybe some other thing I lied to you about that I didn't know I was lying to you about at the time. It'll come to me. All right. Let's dive in, okay? And let's really just do some examples today. And my point in doing this, of course, is so that you learn from physics, but also this process that we go through in problem solving. This is designed to help you get started. I get a lot of messages. Mr. Bale, how do I start this problem? I don't know where to begin, all this kind of stuff. And usually that's a failure of wanting to skip the first two steps and get right to the part where you just kind of do the math, right? But really, where we're doing the math is in the third step. We don't start with math. We start with big ideas, trying to see the problem, trying to understand it, figuring out where we are, where we're trying to get to, and the plan that's going to get us there. And after we're done with those two things, that's when we do it. So I'm going to model this. This is what I use in all the lectures, everything. I will never, right, on an exam or something, dock you points for you didn't do the visualization step or whatever, right, okay? But I might ask you, right, as you're working through stuff, I was like, well, where did you visualize? Where did you strategize? And you can tell me, Mr. Bale, I don't do it that way. That's fine, okay? But if you want to have an easier time of it, okay, this is a time-proven method, okay? Now, some books, some websites, some YouTube videos, they have like a 13-step process. It's just too much. I can't remember more than 3 things at a time, okay? So the 4 is pushing it. I kind of boiled it down to this. So let me model that, okay? by doing a problem, okay, that we call kinematics. This is this is the toolbox. Remember I gave you that sort of analogy that we're going to build a house. We need a plan, we need materials, we need tools, right? These are the tools we're going to reach for after we've come up with a general plan. And so, again, I'm going to start writing some math on the screen, and your brains are going to start shutting off. Try not to do that, right? So I'm actually going to write these on the screen, and then I'm going to write them on the board because we're going to need them a lot today, okay? And your book has got like 6 or 10 of these equations in this chapter. You only need 3. Did the others not work? No, they worked fine. But these 3 will get you everywhere when you're solving kinematics problems in one dimension, okay? And this is what they are. And I apologize for my messy writing. I've tried over the years to make it better. This is actually about as good as it gets, okay? So I'm going to put them right up here so that we have them, okay, to reference, because I'm going to get off of this page. But what does that first one say? Remember I told you that math is a compression algorithm, right? It's trying to take some ideas, okay, and get them together. Liam, did I make a mistake?
No, I just wanted to answer your question of what does it say.
Oh yeah, what does it say? So what does it say?
Velocity is equal to initial
Okay, need to stop. What kind of velocity? How is this one different from this one?
There's initial velocity and then there's velocity.
This is an initial velocity, okay? The way we say this in physics is we say V naught. It's N-A-U-G-H-T, because English is stupid, okay? It means 0. It's an old-fashioned way to say 0. As a matter of fact, if you were born in the 2000s, between 2000 and 2009, okay, 2010, so I was born in the 70s, right? Okay, in the 1980s, 1990s, you can be born in the teens and the 20s. So what happens when you're born in that first decade of a new century? What do they call you? The naughties. You were born in the naughties. I think that's funny. Anyway, okay, so this says V naught. It's a V sub 0, okay? And that symbol means initial. Okay, it means what you start with. So what does the symbol without the naught on it mean? Final. We're comparing, so we start with this. We go, the final velocity can be found, determined, okay, if we know initial velocity and the acceleration and how long it accelerated, right? That's what that equation is trying to tell us, right? It's a tool. Now, of course, if we know final and we don't know initial, but we know these other, can we use the tool?
Yeah.
Yeah, right? Just need some algebra, but it's linking those ideas together. Okay. What does a delta x mean? Change in position, right? I know it's x, but you want to think of x, y, and z as position things. So whatever our change in position, or we can call this the fancy word displacement, right? How far something moves, is going to be determined by initial velocity and time, acceleration, 1/2 and time squared, right? All right, and then the third one, where we start getting some squares, we already know all of these symbols. But the tools tell you, they give you an idea, right, of where they are really, really good. And generally, they're really, really good with the thing that they're missing. What do I mean by that? Look at the third one. What's it missing that the other two have? Time, right? So if you don't need to know time, or time isn't given, then that tool, right, could be the right one. It's like if you know you need to put a nail into a board, don't reach for a screwdriver, reach for a hammer, right? So look at the tool right? It's part of your strategy is figuring out which tool is going to be the right one to use. But don't start here. I know feels like I'm starting here, right? But I wanted the toolbox out. I wanted it open and ready to go so that we can grab what we need, okay? So here's a problem. Now, as I talked about in Thursday, don't sit there and try to write down the problem. Let's really get into this together, okay? And see what we can't come up with. So we've got to visualize first. Visualization involves reading the problem and maybe putting yourself into the situation. And hopefully this is a situation that's common, right? This isn't always going to be the case. A lot of times in physics, I've never done that before, right? So there's different ways to visualize. But here, we're traveling in a car, right? And can you visualize yourself just driving along and putting on the brakes and coming to a stop? What that feels like, what it sounds like. I know this doesn't, Mr. Balogh isn't helping me with the physics, but it is getting your brain, right, into the mode of thinking within, right, the constraints of what the problem is telling us. But even more importantly, there are numbers here, right? There's data present in this problem. And so one way to visualize, and this is a really good way to get started, okay, is to make a list. Make a list of everything you know and everything you don't know. Oh, but Mr. Balogh, I don't know anything. That's going to be a really long list. We are constrained by our tools for this particular chapter, this particular topic. This represents we've got a screwdriver, we've got a hammer, and we've got a wrench. Okay, we don't have a saw, and so we can't cut anything. Likewise, if there is something else like this, if this problem's asking us about the force it took to stop the car, we can't answer that. Okay, that's chapter 5 stuff, right? So we can make a list of everything we could know or not know, and that list is going to come from our toolbox. What do I mean by that? I'm just going to move through the toolbox and say, well, something I could know or not know would be the final velocity. Okay? Something I could know or not know is the initial velocity, the acceleration, the time. Where did I get all those? Read the first one, right? Okay? It's a list of parameters that I could know or not know. Getting to the second one, I pick up this delta x thingy, whatever that is, right? Have I already written down v naught? Yep. Have I already written down time? Yep. Do we know what a half is? Okay. Acceleration, got all that? I'm not seeing any other repeated symbols, or new symbols rather. Okay, it's all repeats. So there it is, right? That is the list of everything I could know and not know. You can write that list down before you even read the problem. If you know it's coming from this chapter, and it's going to involve motion along one line, either horizontal or vertical, you can write this list down. And now we start going through, we look at the numbers that they've given us. And not all numbers are given. Not all numbers are numbers in the problem. Is there a hidden number in this problem?
The hidden number is the final velocity because it's 0.
Which is what? It's 0. How did you know it's 0?
Because it comes to a complete stop.
It comes to a stop, right? So you gotta read. Reading comprehension, right? Okay? If it says it comes to a stop, that's a 0. Okay. So the 3.1s, what is that? That's time. Write it down. That's something I know, okay? The 27 meters per second from the unit, what do you know it is? It's got to be a velocity, and it's where it starts, right? Where we're driving along, and then we hit the brakes. So the instant we hit the brakes, okay, then that is going to be, the velocity that we start with, 27 meters per second. Okay, and as we said, we know it comes to a complete stop, so it's going to be 0, that's supposed to be an S, meters per second, okay? I've run out of numbers, and I've run out of numbers that are just implied. So do I know what the acceleration is? It's not given, and so I'm going to put a question mark. Some people are like, Mr. Balogh, just leave it blank. No. A question mark means I don't know what it is. I think in my visualization that I have not been given this thing, right? And I want to leave a record behind to future me who's going to come back and look at this. What the heck did I do? What did I assume? Right? This is all part of visualizing the problem and organizing the information that we have. So I think blanks are evil because it just means there's no information there, right? But at least a question mark tells me that I tried. Like I thought about it and I think this is something I don't have. What about delta x? Do I know anything about delta x? No. So I'm going to put a question mark on. Okay. So you could draw a picture, right? I'm a terrible artist, so I'm not going to draw a picture. Got kind of this visualization. I'll draw a picture for another one here in a few minutes. But do you catch the vision of what I'm trying to say about a visualization? You want to organize your thoughts. You want to organize the information that you have. You want to come up with you don't have to use mine. Come up with a system that allows you to figure out, right, the things that you can work with. Now, this toolbox does have a fatal flaw, and that fatal flaw is it only works for constant acceleration. If the acceleration is changing all over the place, which is typically what happens when you apply the brake, like when you first brake, okay, your acceleration is probably the smallest it's going to be, but it gets bigger and bigger as you kind of get slower and slower because the brakes are becoming more effective. So we kind of have to, right now, because we're taking baby steps, kind of have to look the other way and go, okay, car brakes on average, acceleration's about the same. Drives the engineers nuts, okay? But if we do it any other way, then we've got to use calculus and we've got to reinvent the toolbox for every problem. I might show you that later, okay? But for now, we're going to stick to the easier stuff. Okay, so I've kind of run out of things to like organize, and now I've really got to get to the meat of what the problem is asking me to do. There's two parts here, there's like an A and a B, right? Okay, so what's part A asking me to do? Find the acceleration. Okay, I got to leave a clue to future me about what the heck is going on. So I'm going to circle the thing that I am going to look for. Again, this is my method. You can copy it if you want. Come up with your own. You don't have to use different colors. I'm just doing that to try to be clear, right? See what's going on. But I know, because there's going to be points in some of these problems where you're sitting there, you're visualizing, you're strategizing, and all of a sudden you're like, wait, what am I doing? What am I looking for? And it really helps to have a star or something on the thing that you're trying to find, right? As just that quick reminder, this is what I'm after. So, what I want you to do right now is the strategy process. I want you to turn to each other and talk about the plan. Look at the tools that you have available to you. Look at the thing we're trying to find and what we have, and figure out what tool would be the best one to use to solve this problem. Go. All right, did you figure it out? Which one of these tools seems most appropriate? The first one, right? Why are the second and third not as good? We don't know delta x, right? And so if we can not deal with delta x, right? I don't want to go and find extra stuff, right? Okay, then it's looking like the first one. So what is the plan? What's the strategy? Can you verbalize what we need to do?
We need to isolate A and then resolve each one.
Okay, so use the first equation, solve it for A. My handwriting stinks, so I often don't write this down in class. If you write down your plan, what it is you're going to do, I promise you that is going to save you time in the future. For the strategize step, you really, and again, I won't do that. I'm going to be a bad teacher. I'm not going to model this for you because my handwriting is so bad. But my plan, okay, I might even say plan. Use the first equation, solve for A. Why am I asking you to write this down?
So that when we look back in our notes, we'll know what we do.
Right? So many people come, Mr. Bale, I have no idea. Can you help me? I have no idea what I did. Right? I look at it, and because I've seen it a lot, I can kind of piece it together, and right? Leave notes to yourself, right? Okay? On your homework about what it is you're trying to accomplish, okay? If the plan fails, if it was the wrong plan, don't erase it. Draw a line through it. Try a different plan. So at least you can see the things that you tried. If you erase it, it's gone, right? Leave that record. It's going to help, okay? Okay, so that's the plan. We have visualized, we've organized our information. And then we have talked about and thought about, this is what I want the acceleration, this is what I've got, and this is how I'm going to get there. Okay, what do we do now? We do it, right? We've got a plan, so execute, right? This is the do it step. This is the part where we do algebra, right? I got to make sure I copied down the first equation correctly. That's usually one of my faults, right? Now, side note, tangent, you're going to get really mad at me for two things. Number one, I work all in symbols all the time. It's a physics thing. We solve symbolically. We put numbers in at the end, okay? So get used to it. Number two, I'm going to skip a lot of algebra, okay? This is not a math class. I'm not showing you how to do math, and I'm not teaching you how to do math. At this point, you should be able, okay, to do this algebra even if I'm skipping steps. What do I mean by that? Well, this equation is going to turn into this. Oh my gosh, what happened? What I didn't show was, what did I do? Subtract V naught from both sides and then divide by T, right? Both sides. I didn't, okay? Because, number one, I've done this a lot. Number two, this isn't a math class. You know, sometimes there's those car commercials, right? And they've got the minivan, and it's going around like a I don't know, mountain road, and they're drifting this minivan around the turns, and the car's doing things it just really shouldn't do. Have you ever seen the little tiny print that's on the bottom of the screen? Yeah, what does it say? Yeah, do not attempt, right? Professional driver on closed course. This is my professional driver on closed course moment, right? Okay, you probably shouldn't do math the way I do, right? Okay, it's almost reflex for me. I'm not trying to do a mic drop or flex on you. I'm just giving you a heads up. There's probably 2 or 3 steps that I kind of skipped over right there because I want to get to the punchline, right? I want to get to the part where we're doing physics again. So my final velocity, I know that number, it's 0. And you can put units in if you want. My initial, 27. Okay. Units are a good check because you can't subtract apples and oranges, right? If one of those was a time and the other was a meter per second, something has gone horribly wrong. Okay? But I got apples minus apples on top is good. And then I'm dividing by my 3.1 seconds. Okay? And some of you might be sitting there going, Mr. Baylor, you're overcomplicating this. Like, this problem isn't that hard. I had it already. Why are you doing it? We started with an easy one, right? Okay, to model what's going on. This process is going to save your bacon over and over and over again when the problems get harder, right? So that I know it can be, Mr. Baylor, just take the velocity, divide by the acceleration, you're done. Yes, that'll get you the answer, but it doesn't teach you about how to conquer everything, right? We don't want to just be able to solve this problem. We want to be able to save Sorry, all of them. Any of them that come along. All right, so we put this in our, did anybody put this in their calculator? 8.7, negative 8.7 meters per second squared. So I'll ask you to do this on exams. This is just a favor to me. We tend to box our answers in physics just to say this is where we got to, right? This is our final result. If I don't see a box, then I kind of have to hunt around and make guesses as to what you think the answer is. So there is an important fourth step in the problem solving method. We visualized, we strategized, we did it. What's the fourth step? Check it. And what do we mean by check it? So there's lots of different ways to check things depending on the context. The very first thing, though, that I like to do is I like to interrogate the answer and say, why is that minus sign there? What the heck is going on? What does the minus sign mean on an acceleration? It's slowing down, whatever, or the acceleration is pointed opposite, right? The direction we called positive. We said the car was moving forward, right? So is that true? Is the car slowing down? Is the acceleration pointed opposite the direction the car is going? Yes, right? In order to go from 60 to 0, what direction is the velocity? Positive, forward, right? So if it's slowing down, what direction is the acceleration? Right? And now we're back to what we talked about last week, aren't we? So, is this a lot? Think about everything I've asked you to do in the last 15 minutes. I've asked you to do reading comprehension. I've asked you to do math. I've asked you to do English and write stuff down, right? Okay? It's a lot of things that are all coming together at the same time, isn't it? Right? So, always interrogate, always look. It's negative. I like that it's negative. If it had become positive, I would have been worried. 8.7. Does that seem reasonable? Well, Mr. Man, I have no idea what a meter per second squared is. I don't know what that feels like. Remember order of magnitude? So the car is going, you can't always do this, but it works here. The car is going, at this point, where we slam on the brakes, the car is going about 30 meters per second, right? And the car, we're going to come to a stop in about 3 seconds of time, right? So if we're 30 right here, and we have to be 0 right here, then every step through, about how much velocity do I need to lose? I'm 30 here, so 1 second later I need to be 20, and then 1 second later I need to be 10, so that I can then in the 3rd second get to 0. Is 8.7 10-ish? Yes. Feeling pretty confident about both direction and magnitude here. Okay? Just plug it in. That's the math answer, which is fine. I don't know about you, but garbage in equals garbage out in my life. Okay? I have proven mathematically that the wrong answer is still wrong so many times in my life, right? By putting the answer back in and it comes out and it all equals and the math teacher just goes, well, you did it all wrong. You did it wrong twice. I was like, okay, right? Like, but better than sort of just plugging it back in and seeing if you get the same number, or put the acceleration in, see if you get the initial velocity, whatever. Is there a different way? Is there another tool that we can use to get to the answer?
I graphed mine.
Oh, you graphed yours. Yeah, that's a great tool for those visually oriented people and have access to graphing calculators, which, I mean, I do. I just do it on Wolfram Alpha, right? So that's a good way. I like it. Can we do something with delta x? What, do you have an idea?
Well, what's Wolfram Alpha?
It's Google for math. Pretty sure that's the URL.
Yeah.
Okay. not allowed to use it on the exam. Use it on your homework. Okay. It's proof that we don't need math anymore. Anyway, mathematicians we need. Mathematics, I'm not so sure about. So, is there a way that we could use another tool? Now, the elephant in the room, the other shoe that's going to drop is part B, isn't it? We're not done. There's another part to this problem. Notice how I compartmentalized, right? I focused on A. I didn't try to get too worried, right, about what was coming, okay? Sometimes a problem's easier to work if you start at part B or C and then come back to A. But we've got a part B. What does part B ask us to do? How far does it go? Okay, so we now know that this is negative 8.7 meters per second squared, right? Okay, so now we can add that to our list, right, of what we know and don't know. We don't have to reinvent the wheel here. The list is still the same. But now they want to know how far the car travels during this period. Turn to each other real quickly and figure out which of the tools is going to be best for figuring out delta x. Go. All right, what do you think?
Second one.
Second one? Do we know the initial velocity? Do we know the time? Do we not know the acceleration? Okay, on the third, does the third one work? We know this, we know that, we can solve for, oh. So both work, but is one better? Yeah, which one's better? The second one, why? No algebra, right? Get it done. Solve for me, right? So what's the plan? For part B, use second equation. Don't do math. Okay? So delta x equals v naught t plus 1/2 at squared. And now I can just plug in my numbers. The initial speed, 27. The time, 3.1. Plus 1/2 times a negative 8.7 times a 3.1 squared. Dropped it on my, Mr. Balogh! Playing fast and loose with the units. What's going on here? Notice how I didn't put in any units. I'll be honest with you, units confuse me when I'm doing numerical stuff like this, okay? But I know I'm going to be safe. Not because I have a master's degree, not because I'm a driver on a closed course. I know I'm going to be safe because I'm using the standard units for all of these things. What do I mean by standard units? Velocity. If you're given a velocity in kilometers per hour, what do you need to do with it? Turn it to meters per second. If you're given a time in minutes, what are you going to do with it? Turn it to seconds. If you're given a distance in miles, what are you going to do to it? Convert it to meters. Okay? Always bring it back to the standard SI unit because all the tools know how to speak SI. It is burned in. It's called dimensional analysis. This always works out to be a distance. Right? A distance equals a distance plus a distance. This meter per second times seconds is going to turn into what? A meter, isn't it? It's hard-coded into the tool. And so I say, and I often use the term, standard units in equals standard units out. And then you don't have to write units down in the middle of your calculation. Put them in the right units at the beginning, you're going to get the right units out at the end. I'm guaranteed to get meters out of this because everything that went in was a meter per second, a second, so on and so forth. It's the power of a unit system. Okay? So that's kind of what I'm doing there. Will I mark you down if you don't put units in your intermediate calculations? No. Right? I'm modeling it for you, right? Okay. Will I go after your jugular if you don't put a unit on your final answer? Yeah. Right? Because it's really important there, right? And if you screw up at the beginning, you're going to be screwed up all the way through, right? So, you decide. All right, this is gonna, did anybody get the number while I was talking? So 42, 41.9 meters. Okay, so this one, how do I check this one? Well, first of all, I interrogate its sign. It's positive. So would I expect the car to move forward during this part where it's coming to a stop? Yeah, okay. So is there any fancy trick for order of magnitude? Like every two, no, there isn't here because there's a quadratic relationship between distance and acceleration and time. So that one doesn't work. But 42 meters, okay? That's, for those of us that speak stupid unit systems, it's about 42 yards, okay? And that's what, like half the length of an American football field? Is real football, is it a 100-meter pitch? Then what is it? No, soccer is measured in meters, isn't it?
Oh, you said football.
I said real football, not American football, right? I think, anyway, it's like half the length of an American football field or half the length of a soccer pitch, okay? So, does it seem reasonable that a car could come to, going 60 miles an hour, could come to a stop in half the length of a football field? Yeah, it's not, I mean, if it were 6 football fields, I'd worry, right? If it was stopping in the width of the end zone, I'd be like, right? But that, based on my everyday experience. Now, you can't always go to everyday experience, right? I mean, you don't have experience with what's going on with the problem, so you've got to find another way to check. But there is another way to check. Now that we've got that distance, where can we put it to check? Right? Our calculated position, our calculated acceleration, and and we can put in the final speed and maybe, no, we'll just put in the initial and see how close we get to 0, right? We may not nail it. It might be a little close to 0, right? Because of round off error or whatever, right? But that would be a great check. You can use that tool to check those things, right? So there's ways to be absolutely certain about your answer every single time. It usually just involves working the problem. Okay? I won't model that check for you. I've been doing this one for years and nobody's corrected me yet. Okay, so it seems pretty reasonable. All right. What I would like you to do right now is with each other for like the next 2.5 to 4 minutes, I want you to begin visualizing this problem. And I kind of expect you to get a little bit stuck. Okay? So I want you to turn to each other right now. I know you barely even read the problem, but just turn to each other and start visualizing. Figure out what numbers go with what and what you might have to do to come up with your lists. Go.
They're not going to be
All right, pause right there. Where are you having trouble? Where are you stuck? Where? Delta X?
T.
T? What does this look like? What is the, where does the negative 8.7 go? We don't, but which accelerate?
Acceleration for the car in the front first.
Wait, there's two cars? There's two cars! Ah! What do you do? Make two lists. Right? Mr. Balogh, how was I supposed to know that? You weren't, but now you know. Knowing is how you know stuff. Right? If you've got more than one object in a problem, you need more than one list. You want a list per actor, per object. That's important in the problem. This problem, I might even start drawing pictures. Okay? I start with two cars, and they're 10 meters apart from each other, and they're both going 27 meters per second, right? In that direction. And which one of them has acceleration? The front car, right? The front car's acceleration is negative 8.7 meters per second squared. Okay, it's initial velocity. These are all initial velocity. Okay. What's the acceleration of the car in the back? It continues at the same speed, right? Which means its velocity isn't changing, which means its acceleration is 0. Again, one of those implied things. They didn't say it was, right? But they did tell us it continues at the same speed, so they're asking us to understand that concept. All right. No lists have been made yet. I'm drawing a picture here, aren't I? Right? Which is fine. If you want to attach all your information to pictures, great. Okay? I'm going to kind of do both here. But really, I kind of want to give some labels here so I know what I'm talking about. So I'm going to call this car number 1, the one in front, and I'm going to call the car in back car number 2. So I can just refer to them really quickly, right? Okay. So car 2 here in the back. What do I know and not know? Do I know how fast car number 2 is going in the collision when they hit? We do? It's 27, right? It never changed its speed, right? Okay. So it hits the first car at 27 meters per second. Okay. Do we know how fast it was going initially? 27 meters per second. Do we know the acceleration? Yeah, it's 0. Do we know how long it took? No. Do we know how far it went? Not 10. 10 is how far apart they start from each other. But delta X is how far car number 2 went. Do you understand what delta X is? Delta X is for an object, right? In this case, car number 2. We don't know if car number 2 went 300 meters, 2 meters, right? We don't know how far it traveled before it hit. We do know that they start 10 meters apart from each other. There's kind of a clue as to what we need to do with this, but we're going to leave it alone for now and say that we don't know. Okay, car number 1. That, wow, is really far away from that list. Okay, car number 1. Do we know the final speed of car number? How fast car number 1 is going when it gets hit? Yeah? No? 0? Does it say that the cars come to a stop when they hit? No. So we can't make that assumption. It's a delicious one to make because zeros are happy, but because it makes math easy. But they told us nothing about how fast they're going, and they don't say that they come to a stop when they collide. Don't know. So you're going to make that mistake a lot, right? You're going to assume something is not true. How are you going to make sure that that mistake gets flushed out as fast as possible? You can only read so close. Practice, sure. Make the mistake enough so that you learn not to make it. hopefully something that you are learning right now is that you can make mistakes faster when you're talking to each other. Right? When you have ideas to bounce off of each other. Imagine, right, if you said, hey, what'd you get for the final velocity car number 2? Oh, it doesn't say anything. It's probably not 0, right? You're like, oh, yeah, that's right. Instead of assuming it's 0, going through the whole problem, solving all the math, and only to find out that the red box of doom has come up, right? So really, bounce ideas off of each other as fast as you can, right? That's going to help you. One of these is in, do we know the initial speed of car number 1? Yeah, 27. Okay, do we know the acceleration? Yeah, it was on the picture right there. Okay, do we know how long? No. Do we know how far? No. All right. There's 4 question marks on the screen, which is now making me nervous, right? Okay. And we haven't used the 10 meters yet, right? So with not knowing delta x and not knowing t, we don't. Okay. So what are they not asking us to find? Of everything we know and we don't know, what are they not asking for? Delta x, right? They don't want, and final velocity. That's good. We don't want to know delta x, right? Okay. So ideally, we don't want an equation that has delta, because if delta x is an unknown and they don't want it, that's time, could be time wasted. So the second and the third have delta. So first one, can we use the first one to do anything? By the way, what do we do? What am I doing right now? What step am I on? Strategize, right? We've kind of visualized a little bit. Now I'm going to strategize. I'm trying to figure out. This is key, right? This is where you go, Mr. Bill, I don't know what to do. I don't know where to start. Let's start with visualization and strategy, right? So the first equation. Does the first equation help us with car number 1? Well, we know the initial, right? We know, but we don't know time and we don't know finals. That's 2 unknowns, isn't it? Yeah. For car number 2, does it help us? Okay, so 27 equals 27 plus 0. True, but not useful. That's how you know it's mathematics. The math majors didn't die. Okay, all right. So that's not helping. Okay, now what? We know the second and the third. Can we don't know that. And again, we don't know the time, so we can't solve for delta x. Yeah. Substitute? Like, okay, so are you saying that there's some things that are the same here? Is the time the same for both cars? Yes. Right? The amount of time that transpires between when the first one hits the brakes is the same for both cars. Okay, so that suggests that maybe we need to use the toolbox twice. Like once for each car, and then like the time, maybe we can substitute the time and figure out something. Okay, I kind of like it. It's a good idea. We haven't used that 10 meters yet. Sometimes not every number is useful. But we really got to ask ourselves, what's going on with the 10 meters?
We could break delta of x into x minus x naught.
Yeah.
And then use x naught.
Remember, this is a good trick, okay? Don't forget that the delta means something. What does the delta mean? Yeah, it's a change, right? It's a final and an initial difference, isn't it? A change. And so we can write down, we can break up this delta, okay? And what we need to do here is we do need to decide some initial 0 point. And it's going to be different for the 2 cars. We can put one of them at 0, but the other one we can't put at 0. We got choice for 0 is just once. Okay? So where do we want to put 0? The front car or the back car? Back car? Fine. Doesn't matter, actually, as long as you're consistent with your choice. So if we say that 0 is right here, then what is the initial position of car number 2? We put 0 at the back car. It's 0, right? We set that point to be 0. We don't know where its final position is. Okay? Now, what is the initial position of the car in front? It's not just 10. It's plus 10. Why am I being insistent on the sign? It's in front of my 0. It's in the positive direction. What if, at the risk of confusing you, what if we had put the 0 at car number 1? What would the initial position of car number 2 then be? Negative 10. Yes, no? Yes. Why is it negative 10? It's on the left-hand side of my 0 point, right? And that's important. You'll actually come up with exactly the same answer either way, as long as you make sure to be correct about the locations of things. You can actually put 0 wherever you want, and as long as you're consistent with your directions, it'll work out. It's easier to put it on one or the other, and probably easiest to put it on the carbon. But easy there is a relative. It works either way. Okay. So that's why I put the positive in thing. Like I thought about it, right? I'm like, okay, it's on the positive side of 0, 10 meters away. Ms. Balogh, how does this help us? Because we still have some unknown things, right? Okay. But there's something I do know about delta x. So delta x has now become a little bit more useful. And so as a strategy, as a general strategy, when you've got a situation where you've got two objects and they're moving and they're going to hit each other, there's something we know about their final position. It's got to be the same. They're hitting each other, right? They come to the same place. So if time is the same and final position is the same, I'm looking at number 2. It's got that position, it's got time. I want time, I want to get rid of position, but we've got crosstalk between the two objects. And again, I know you're sitting there going, there's no way I could have ever known this. Well, that's not quite true, it's in the book. Okay? But now you know when you are presented with a situation where you've got multiple objects interacting, you've got this trick in your bag. Look for the things that are the same. See if you don't know what they are, but you know they're going to be the same thing eventually. Can we leverage that? So the strategy here is going to be write down the second equation for both cars. Okay? So delta x equals v naught t plus 1/2 at squared for car number 1. And then for car number 2, I don't know if those colors are different enough. I'm going to do the same thing. I'm using a new piece of software. Is this big enough? You guys can see it okay? You're younger than me, so your vision's better. How's my handwriting doing? Is it too messy?
No, it's physics handwriting.
Physics handwriting? And you're being nice. Okay, thank you. Please give me feedback as to whether or not this is either isn't big enough or whatever, right? Not clear enough. I can turn the lights off and then everybody goes to sleep, right? So I know contrast can be a little bit of an issue. So please just give me feedback. Let me know if this is working for you or not. Okay, so I'm gonna write these down. Okay, so the delta x for car number 1 is an x final minus 0, right? Final minus initial. Equals 27 times t plus 0, doesn't it? Because the acceleration of car number 1 is 0. And a 1/2 times a 0 times a t squared is going to be a 0 anyway. Nice. Okay. So, over here, this is going to be an x final minus a positive 10. Again, it's a difference, right? It's a delta, a final minus an initial. Equals 27t plus 1/2, supposed to be a 1/2, that was not a good 1/2, 1/2, running out of room, negative 8.7 t squared. Whew, sorry. So let's clean this up just a little bit. Car number 1, x final equals 27t. And then over here, x final minus 10 equals 27t plus 1/2 times negative 8.7 t squared. Okay, I've got those two things. I'm going to move my negative 10 over, plus 10 plus 27t minus 1/2 times 8.7 t squared. Okay, now that I've got car number 1 with x final equals something, and car number 2 with x final equals something, what can I do? I can set them equal to each other, right? The final positions are the same, so I can just set those equal to each other and see what happens. Notice how visualization, strategy, and doing it can meld together, right? I'm feeling my way forward on this one, so maybe I've got to do some algebra along the way to see if my plan is going to work. Don't think of them too rigidly. Start with visualization, but be willing to go forward and backwards, right? Just try not to start with the tool first. That usually gets you in trouble. So we're going to set these two equal to each other, which means 27t is going to be equal to 10 plus 27t minus 1/2 times 8.7t. I lied and I didn't do it in symbols. Okay, so I've got 27t on both sides. So they cancel, right? Move the 10 over. That's a negative 10. Move the multiply both sides by 2. Multiply both sides by 1/2. Divide both sides by 8.7. Told you I did algebra quickly. Mostly to get the pain over with. This is a t squared, by the way. And so I'm going to take a square root, okay, of 20 over 8.7, which is going to give me a plus or minus 1.52 seconds. We'll pick the positive one now because time is going to be moving in the forward direction. So about 1.5 seconds for these cars to come into contact. So if somebody's driving behind you with a cell phone and they're distracted and you slam on the brakes and it takes them a second to realize that TikTok is not the most important thing right now, do you think that they can have a sufficient reaction time to start slamming on the brakes with the 1/2 second left? Yeah, there's going to be a collision, okay? This is why almost every morning on the 41 as I'm coming in and somebody is like tailgating me, right? I just want to have police lights, turn them on, pull them over, right? And give them this lecture. Show them the data, right? You don't have time to stop if I have to stop. Suddenly. All right. How are you doing? Yeah, you need a lot of practice. Your brains are probably full, so I'm going to fill them some more right now. Okay, right? But what I want to do, okay, is we're going to kind of do the mechanisms of a quiz, but this isn't a quiz. Don't get your quiz sheets out. Okay? Because what I want to do is I want to show you something. I want you to learn sort of the kind of thing I expect you to know just from reading. Because now I'm going to go into vertical motion. It's still one dimension. It's just we're going to do it straight up and down. Okay? So as soon as I put the question up and you read it, I want you to just turn to your neighbor and discuss the answer. Okay? So just real quickly, talk to each other, figure out the answer to this question. You should have been able to know this from the book. You're getting, I think, a little bit of a sense of my sense of humor, right? Okay, because the answers are definitely not C or D, right? Okay, those are just silly, right? So, what's the answer? It is B. That would be something, if you've gone over the chapter or if you've watched the videos for the chapter or something, it comes out in that information, right? So really, what should you be trying to pick up on before coming, right, to class so that you know you can be prepared? Concepts, ideas, definitions, okay? Those are going to be critical going forward. For last week and today, I've been holding your hand, sort of introducing you, getting you used to all of these ideas, but I'm going to begin offloading, okay, some of these more basic ideas and definitions, right? Kind of want to know what those definitions are before you come. I'm not saying you need to memorize them. I'm just saying that somewhere along the line you should have picked up that free fall just doesn't mean falling. It has a very specific definition, meaning gravity is the only force acting on it. So that means that we can't have any kind of air resistance, right? Because air resistance wouldn't be gravity only. Okay, I've got a binder and I've got a piece of paper, okay? And I'm going to drop them at the same time. According to Galileo, all objects accelerated exactly the same rate. That one right there, he actually came up with a slightly different number. This is the bottom one, okay? So if I drop both of these things, which one hits the ground first? That is not what Galileo said. What's the engineers in this room? What's your problem?
They both have the same.
They do?
Yeah, let's see.
Just do the experiment, right? Galileo's wrong. Right? Okay, we proved he was wrong before the paper hit the floor. Why is this not free fall? Because there's air resistance, right? So, yes.
So like, is skydiving like misnamed when they say they're free falling?
Yeah, they're not in free fall. It's skydiving, which I did this summer. My father-in-law turned 80 and wanted to jump out of a plane. Right? Is not free fall because skydivers reach terminal velocity. They're not speeding up, they're not slowing down. It's just wait, what's terminal velocity mean?
The point where
The speed at which you die.
Then the maximum speed.
You have to say it that way. It's like the maximum speed that something can go in a resistive medium. Right? So if there were no air and a skydiver jumped out of a plane, would they ever stop accelerating? No. Until they pulled the chute, which is not gravity again, right? Parachute opening, the air resistance. Not? Okay, so we need to take all the air out of this room. Lucky for you, I brought a vacuum pump. Okay? So, we're going to close the doors. We're going to hold our breath. It's going to take about 56 minutes to evacuate all the air in this room. We good?
Yeah.
Yeah, let's go for it.
not together.
Yeah, that's better than whatever you've been teaching me, Mr. Baylor. I'll take that. Now, I've got a tube. It's got a little thing I'm going to hold on here. And inside this tube, there's a penny and a piece of white, I don't know if you can see it, there's a piece of like white foam, okay? And if I turn this over, which one wins? The penny's winning, right? It's very slight, but the foam is kind of lagging behind, okay? So what I'm going to do is I'm going to suck all the air out. Suck all the things directly into the okay, there we go. Okay? We're going to suck all the air out. Ooh, the sound changed, didn't it? Okay, that means that the pump is evacuated as much as it can, okay? So in theory, I've removed all of the air from this tube, right? I want you to try and see which one hits first. You ready? Reset. And here we go. What does it look like? white one's not lagging behind anymore, is it? Okay. I know it can be hard to see from the back. Okay. But they are in fact hitting at the same time. Okay. So hopefully there, we got the experimental evidence. Galileo was right. All things, so if we go out and we throw an elephant off the balcony, we throw a mouse off the balcony, ignoring the air resistance, which one hits the ground first? They both hit the ground at the same time. Gravity accelerates all objects at exactly the same number. Gravity pulls differently. Which one weighs more, the elephant or the mouse? The elephant. Gravity pulls on the elephant more because it has more mass. The mouse, gravity pulls less because it has less mass. But they'll always work out to be this acceleration. Yes?
How did you determine that without a vacuum?
Yeah, how did he determine that without a vacuum? I paid him that. I didn't. I'm going to repeat this experiment, okay? And this time, I'm going to make sure that the paper and the binder both hit the ground at the same time. Without doing any evacuation of the air and all that kind of stuff. These two will hit the ground at the same time. Are you ready? What did I do? I made air resistance a non-factor. In other words, I made sure the air resistance was the same across both of these things, right? By letting the binder sort of take the brunt of it. But did you notice how the paper just followed it? Pretty cool. And that's kind of how Galileo got to it, right? He also used really round objects, and round objects tend to not be bothered with air resistance. You get enough mass, air resistance becomes that word that I can never say that starts with an N, and it means it's small. It doesn't matter. Thank you, negligible. I always have to hear it first. Okay, negligible, fancy word for it doesn't matter. And we do that a lot in physics. We're like, it doesn't matter. And the engineers go, yeah, it does. Okay. Oh, I had a quiz? I don't remember that. I do have a quiz. In the last 5 minutes, we're not going to do the quiz. Maybe I'll do the quiz later. In the last 5 minutes, what I want to do is I want to get to an example really quickly so that you can kind of do everything in chapter 2 now. Close that one. Okay. So here's our problem. We'll go kind of fast on this because I'm running out of time. Apologize. Okay. But here, just hold on for the ride here. I'm going to model the problem-solving method, okay? And I know you haven't read the problem, but it's all right. You can go read it later. My list. That's what it kind of started with, right? But now, instead of delta x, I'm going to use delta y. Why am I going to use delta y? It's going up and down, right? Okay? And it's just, can you use delta x? Sure, I don't care, right? But you've been taught that the vertical direction is y, so why not? Yeah, we can use delta. But has the meaning of the thing changed? No, it's still a change in position, right? It's just now we're doing one-dimensional vertical motion as opposed to one-dimensional horizontal motion. Because this thing is in free fall, the bowling ball, whatever it is, right? Okay? When she lets go of it, when the pilot lets go, what is the only thing, the only force acting on the ball? So what do you know about its acceleration? You know the acceleration has a magnitude of 9.8 meters per second squared, and what direction is it pointed? Down. Pointed down. So what are we going to put in front of it? Negative sign. How fast is the bowling ball going when it is let go? It's going at a rate, a magnitude of 4.3 in which direction? Up, right? The balloon is moving upwards when that bowling ball gets dropped. So the bowling ball gets dropped, it goes up, and then it turns around and comes back down because is gravity pointed down even though the ball is going up? Yes. Right? So it's going to slow down, come to a stop, turn around. Okay. All right. Do we know how fast the bowling ball is going when it hits the ground? No. You're like, it's 0. Yes, but that's not free fall, right? Coming into contact with the ground is no longer just gravity acting on it. It's now the ground is acting on it. So we can't, eventually it's going to be 0. But this question is saying, okay, in the instant, like right before it hits the ground, how fast is it going? Do we have any information? 0. Question mark. Okay? I shouldn't have said 0. We don't have any information. Do we know how long it took? Do they tell us is there any seconds up there? No. Is there any implied words that would tell me how long it took? No, there's nothing up there. Again, I don't know. And then, do I know how far? Like from beginning to end, not the distance it traveled, but the displacement. Do I know the difference between where it started and where it landed? There's another number, 56. Is there a possible way to use it? Yeah, we could break it up into initial and final, argue about where 0 is, but it actually doesn't matter. Because the answer here is not 56. Because that's just a magnitude. What direction did the object displace? Your choices are up or down. It displaced down. It ended up lower than where it started. That's a downward displacement. And according to you, what direction is down? Negative. I said according to you because in chapter 5 we're going to turn that around. So what are we going to put on our delta y? A What happened? We're going to put a negative sign. Do you notice that I'm being really serious? Is that negative sign important? Vitally important. Because if you don't put it on there, then what you're telling your tools is that this thing is let go at 4.3 meters per second, is accelerated downwards, but then ends up 56 meters higher than where it started? You try to do that, and you're going to get imaginary numbers out of your square roots. And if you're getting imaginary numbers in your calculations, you are doing imaginary physics. You're going to come up to me, Mr. Balogh, this is all wrong. And be like, well, you didn't get the minus sign. You're like, oh, well, it's just a minus sign. Can you give me credit? I'm going to be like, no. It is the minus sign. The master minus sign. The infinity stone of minus. The minus sign that binds them all. And in the darkness binds them in the land of Mordor with a shadow. It is the one minus sign. Because if you don't give your tools the correct data, the correct physics, they're just going to give you garbage. It's going to be bad. These minus signs could kill. Think about them. Always interrogate your data. Is it positive or negative? How do I know? You're going to make a lot of mistakes. You're going to be nice to yourself, but you got to make those mistakes as fast as possible. And how are you going to make your mistakes as fast as possible? Working with each other. Practice, working with each other. And you'll get there. You'll make it. Full brains. Good luck in the rest of your classes today. I will see you on Wednesday. Chapter 3 on Wednesday. I actually kind of finished all Chapter 2's content, except for that quiz. But Chapter 3, complete Chapter 3 on Wednesday. But I'm only doing the first 3 sections, right? We're going to leave the last 3 for later.